If there are more questions, ask me. Okay? All right. So again, we discussed breadth first search, and we talked a little bit about the running time. But today what I want to discuss is really what is the output of BFS and what is sort of the main theorem about BFS. So let's maybe go back to the outputs of BFS. So as we discussed, BFS, the input is a source vertex S, the output are these two arrays. Right? So what I'm going to tell you right now are the main properties of these two arrays or lists, and then we'll talk about how one proves those properties are true. So while I think hopefully this is, this often confuses many students, which is like, how does the predecessor array actually store a shortest path tree? So this is just something I want to talk about. If there are any questions, again, ask me. So you look at this sort of, so predecessor V. So we interpret as a shortest path tree. Okay, so just to explain what this means, so if you think of S is the source, there are going to be some vertices whose predecessor was S. Right? So who are these vertices actually? Yeah? Yeah, but who are those children in the graph? There's one word that I'm looking for. Yeah? The neighbors. The neighbors of S are all going to be the children in this tree because all of them will have S as a predecessor. Right? So you've got a bunch of vertices here, and so for each of these guys, predecessor V is equal to S. And then you've got a bunch of vertices, which I'll call U over here, so that the predecessor of U is equal to V. So on and so forth. So even though you're storing this just as an array, the way to think about it is as if it's a tree. Does that make sense? So why is this a tree? What makes this a tree? Yeah?
We may not be visiting V again, let's say, because we have to check on the
No, it has nothing to do with the algorithm itself. It just has something to do with the fact that predecessor is an array. Yeah?
I have a small question.
Yeah, go ahead.
That's a V, right?
Predecessor of U is equal to V. Yeah, sorry. But yeah. Yes, U. In the mask, yeah.
Because it's hierarchical, there's an order to it.
Yeah, why is there an order to it? I guess. Why is it a tree? Yeah?
It doesn't start cycle
Why doesn't it have a cycle? Exactly.
because it's not completely connected.
Not entirely. So you're right. So it doesn't have a cycle. But why doesn't this structure have a cycle? Yes?
It has a root node.
Not yet. Yeah.
You're storing friends within friends, like the arrays within the array.
But I mean, in the end, it's just one array. Yeah?
Each node only has one parent.
Exactly. Bingo. That's the answer, right? Each node has only one parent. Right? So there's no way it's not going to loop because there's no one over here has two parents. The only way you can loop is if someone has sort of two parents. But, well, the way this functions, everyone only has one parent. Right? So because you have one parent, you can keep following your parents up. You're never going to end up in a cycle. You always end up at the root. The root is S because S is the only node over here whose predecessor is null, except for nodes that are not visited. Okay? So why is this relevant for, let's say, the programming, the coding up of BFS, is that if you think of BFS just returns that array and that's it, and you want to extract a path from it, the way you do that is you start from a node and you keep following the predecessor. So it's a very convenient way of representing everything. It's like a compact representation, right? So you don't have to actually create a tree data structure and construct a tree data structure. It's kind of implicitly stored in this way. Does that make sense? Okay, good, right? So you're all circling around the thing. There's no cycle here because, and I'll write this down, each V has exactly one parent, and that parent is predecessor of V. Okay, good. So now what I'm going to state is what I'll call the main theorem. This is what I'll call like the BFS theorem. Okay, so this is just a formal way of stating what happens when BFS terminates. And when you read that statement, it will sort of tell you everything that you need to know. So when BFS S terminates. So by the way, I hope everyone saw, so the slides, whatever I write, I scan and I put up, and it's on the course website. Right? So I put a link over there. Okay, so I'll do that with every lecture, and the reason I do that is because when I was a student, I could not listen and write at the same time, although some people can do it. So I found that very difficult to do. So I said, okay, when I teach, I'm always going to scan and put everything up. Okay, so when BFS terminates, the first I want to say, what are the properties of the visited array? So I'll say visited V equals true if and only if what? What is the condition so that visited V is true? Yeah. Yes. There exists a path from S to V. Right? So if there exists a path from S to V, you'll visit, and vice versa. If you visit V, then there must be a path. Right? So does everyone understand what if and only if means? It means that they imply each other. Okay? So if and only if there is a path from S to V, this is also equivalently saying that S is connected to V. And I'll just say this again here. The graph is undirected. So S being connected to V is the same as V being connected to S. So a path from S to V means a path from V to S. When it's directed, then things are more complicated. And when we talk about DFS, we'll talk about things in undirected graphs. For the sake of this discussion in shortest paths, it's useful to think about undirected graphs. You can generalize this to directed. Okay, so that's the first statement. The second, predecessor V is null if and only if what? Yeah. Yeah, sure.
I don't get it. If there could be a path, but I haven't visited the node, and there could be a path.
No, when BFS terminates, when it finishes, okay, so.
Oh, is that we have the path? It could be not that there is a path, but we already have a path.
So if you have a path, that means there exists a path, right? There is a path in the graph.
Yeah, but not the other way. It could be a path that I don't have right now.
Okay, good. So you might not have this path. You might not have discovered this exact path, but still visited V is going to be true because you would have visited by some other path.
But it is not true until I visited.
So
It's just semantics because
no. This is let's clarify this, right? So there is a distinction between what happens with BFS at an intermediate step and what happens when it terminates. When it terminates, I'm saying that imagine that you finish this, and I haven't written this explicitly, but predecessor and visited are like the return values. So I am talking about the behavior of the return value sort of at the end. which is different from what happens in between. Does that clarify a bit? It's sort of what happens when it terminates. So maybe the right way, I didn't write this explicitly over here, but I'll sort of add this. I mean, I did say it because I said, where did I put that? Paper. Let's lose track of. It must have been somewhere where I said like the output is the predecessor array. Right, so sorry, there it is. Yes. Remember, so I said the output are predecessor and visited. So these are like return values. Okay, all right. Okay, so again, maybe just to reinforce that point, that doesn't mean that BFS found that specific path. It just means there was some path, right? The reason why this is important is that there are actually there are a huge number of paths in the graph. BFS is not going to find all of them. Because if BFS tried to find all paths, it would take forever to run. Okay. So when is predecessor null? Yeah, go ahead. Okay, so if V equals S, true. Is that it? Yeah.
Maybe a separate component.
Separate component. So what would you write here? Because we haven't even defined component. You're right. Like I have to define what component is. So what would I say? Yeah?
When you can't reach the V from S.
Yeah, so if and only if V is equal to S, or there is no path from S to V. Right? Or I'll say V is not connected to S. Yeah? Okay. And now, the third and sort of maybe the most important point, the one that we really care about, is that, say, for V connected to S, the path V, predecessor of V, predecessor of the predecessor of V, so on and so forth, all the way back to S. Why does it have to go back to S? Because by the second step, the only vertex connected to S, whose predecessor is not null, is S. So if you keep following predecessors, so maybe let's unpack the statement. The reason why I need to write statement 2 is because otherwise statement 3 won't make sense. How do I know that these aren't null? I go back to the previous one. I say, look, if V is connected to S, then the predecessor is not null, so there must be a predecessor. And this is also connected to S, right? Because if V is connected to S, then this is also connected to S. So its predecessor cannot be null until at some point you bump into S, at which point the predecessor is null. Then you can stop. So to make sense of statement 3, you need statement 2, which is why I've written it in this form. Okay? So this path is a shortest path from V to S, and because this graph is directed, it's the same thing as saying from S to V. Yeah? Yes, there are many paths that are not shortest paths, and for example, let's look at this graph over here. Let's look at 1 and 5.
Yeah, with that I get it, but you said that there's only one predecessor.
Correct. So this is a shortest path. There could be other shortest paths in the graph. BFS does not find them.
But if there's only one parent per node, how could that be?
How could there be multiple shortest paths?
Yeah, if there's just one parent per node with that.
Okay, so for example, look at this graph. How should I do this? Huh?
1 or 5.
These are neighbors, not parents. Parents are from the predecessor, which is the output of BFS. There are multiple neighbors which are in the graph. But the parent is based on the output of this procedure.
Okay, yeah, I got it.
Okay. So yes.
I'm confused about theorem 2.
Okay.
Because you break early, because when you find the destination, you break early.
Forget that. I'm not doing that version. I'm doing the full BFS running all the way to the end. Right? I'm looking at the code that I've written. When you break early, then you're right that 2 is not going to be true, but it's going to be true in one direction. It's a little bit more subtle over there. So let's not worry about that case for now. Just deal with this one. So is this clear? Right? So this is like, so if you're just programming the algorithm and someone gave you this theorem, this is all you need. Right? Because you would basically say, okay, so now I know I know what the output is doing. And this is a way of sort of formally stating what the output is doing. Instead of just, yes?
So just like some clarification.
Sure.
B is kind of based on, we've already got the shortest path, and it's not for all the possible paths.
Sorry, say that again.
So the BFS tree, and like when we the predecessors, that's all based on we've already got the shortest path, and those are all based on the shortest path, but not for all the possible paths.
It's not all the possible paths, nor is it all possible shortest paths.
So it's already based on the shortest path.
Maybe I would flip it and I would say that, okay, so the reason is, if you look at depth first search instead of breadth first search, right, where essentially instead of the queue you have a stack, you also get a tree. You also have a predecessor array. You have a visited array just like this. It gives a tree, but that tree is not a shortest path tree. Like just because this is a traversal procedure, just because a traversal procedure outputs some predecessor array doesn't mean that it's always going to find shortest paths. So the important thing that we want to learn, if we want to understand more deeply, is why is this finding shortest paths? Why is it the case that if I put a queue, I get shortest paths, but if I put a stack, I don't? And this actually goes back all the way to the question that I asked at the very beginning, which is, how do you know that the output is correct? How do you argue that, like, remember we discussed this problem, right? We said from S to T, and we had this whole discussion of, well, because look at the neighbors of T, and based on that, you can infer that the shortest path is actually, 3 or 4. But in general, if you want to argue that BFS finds shortest paths, then you have to sort of make this argument. So first, it's almost like we want to state down mathematically what is it that BFS does, and then we kind of prove that that is correct, and in that proof, we'll see why the queue appears. Is this sort of making more sense now? Am I going too slowly? Raise your hand if you think I'm going too slowly. Okay. Am I going too fast? No? Okay, it's fine? All right. It's funny, someone was saying that, so I guess you are the first generation of students who actually have done everything in person, right? Like COVID started when? Like when you were undergrads? Like just at the beginning? Freshman year. And then after that, everything opened up, right? So you're all more well-adjusted, frankly. There was actually a discussion in the faculty Slack channel like that, oh my God, the classes are so much better now. And then it's like, oh, it's because like this is the first generation that actually was able to, sort of actually did college after things opened up, or pretty much at the same time opened up. Okay, anyway. Yeah, question?
Sorry, I would ask to witness some.
Yeah?
But you say number 3 that if B is connected to S, that path is a shortest path.
Correct.
But you also say that there could be multiple paths.
So I think you're conflating two things. There is the path in the graph, and there is the path given by the tree. There are two different things. The path given by the tree exists in the graph, but there are paths in the graph that are not in the tree. I'm going to do a visualization of BFS, and hopefully that will clarify some of the things.
Well, I get the BFS algorithm. I saw it last quarter, but the definition that you're giving, something is like, I don't know, not much. And maybe if you can go to the previous slide with the graphs.
Yep.
That one. Let's say the path that we want to find a path from 5 to 4 in the 1000. We can start from 5, then go to
12.
yeah, because this is red first now. Yeah.
You will go 4 to 1 to T to 5.
Yeah, but we can make another path.
Sure.
But that one, yeah, we can make another path.
You can make many paths, but BFS is going to find a path which happens to be the shortest path.
I think that's where I'm conflicting. Because, yeah, BFS can find it, and that's true. But what you're saying in your mathematical definition is not saying that. It's just saying that if there is a path, that's the shortest path. That's it.
That's not true. So that's saying predecessor is output. This array comes from the BFS. The predecessor array is not part of the graph data structure. It's the output of BFS. The neighbors are the graph data structure. Now, just to be clear, this pred and visited are outputs of BFS.
So,
Let's do a few examples and hopefully it'll clarify it.
the thing, if I get an example, I'll get it. But number 3 is just precondition, and in that this has to be through a BFS algorithm for that to be true. So number 3 is not defining BFS. It's just that applies only if BFS.
Yes, this is only for BFS because it says that the output of BFS are these two arrays. Did you come and talk to, let's take this offline. Talk to me, I'll explain it. Yeah. Okay, so any questions about this? Now for the difficult part is why is this true? Right? Do you see that it is not at all obvious that this should be true? Yeah?
I mean, it seems kind of obvious that it's true.
Okay, all right, interesting. Yes, why?
Because each layer of the tree is exactly one step of neighbors away from, like, so if you draw the tree out, each step away on the tree is exactly one layer of neighbors away.
So how come it's not true for depth first search? Because depth first search also has layers.
Because it's not iterating, like, it's not going through every neighbor, adding each neighbor, then going to every neighbor. Like, you can't say that same property is true about the tree.
I mean, essentially, yes, sort of, kind of. But how does one make that argument like sort of a watertight mathematical argument? It's surprisingly difficult to do that. I mean, yes, intuitively, you're like, it's looking at neighbors and neighbors of neighbors. Of course, if you put weights in, then it's not true anymore. If you go depth first, it's not true anymore. So what is it about the current setting that makes it true? The reason we need to understand that is if you now want to do it for weights, then you understand where things fail. Like, and this is exactly what I want to get at. So your argument, which is essentially the essence of what's going on, is really dependent on the fact that there's a queue. So, okay, so is this, at this point, everyone following? And maybe what I want to sort of emphasize is why it is difficult to argue that this is true. Even though you might intuitively kind of see that, yeah, it sort of makes sense, right? If we wanted to mathematically sort of assert this, we need to do something else, or there's a step towards this, and it's called discovering a loop invariant. A loop invariant. So I'm gonna write this down. So but first, any questions about if the statement is clear? Okay, so now let's proceed. how to prove, and by mean I prove mathematically, right? How do you know that this is actually correct? So what we need to do is to discover something called a loop invariant. So what is a loop invariant? It is a statement that is always true at the beginning, or depending on how people do it, sometimes we'll say or the end. That depends on phrasing. Of a loop. Okay, so it's some sort of mathematical statement that is true at the beginning or at the end of a loop. And so if you look at BFS, I mean, you can think of there are sort of two loops here, but this is sort of the main loop, the queue, right? When the queue is being dequeued. So what we need to do is we have to discover something about what the data structures, which are queue, predecessor, and U, look like at the beginning of each loop. And we kind of understand what happens so that eventually we chain it all together and say, okay, at the end it gives us what we want. Yeah?
We're looking at predecessor, visited, parent.
And predecessor, so the only data structures that are internal to the algorithm there are three of them. There's the queue, there's predecessor, and visited. Now, what the BFS theorem does, which I have here, this only talks about visited and predecessor at the end, and so the queue at this point is trivial. The queue is empty. But to understand why this statement is true, you need to understand how this was constructed, which is talking about all the intermediate steps, and this is where the queue enters the picture. So the loop invariant, and I say discover because actually discovering the loop invariant is very difficult. It requires actually a fair amount of creativity and understanding to see what is the pattern. And once we discover the loop invariant, the way that you prove this is the proof is done by induction over the number of iterations of the loop. Okay? Okay, so the best way to actually, I mean, I can write down the loop invariant, but then you won't appreciate why that loop invariant is true. So the best thing to do is to actually run through BFS. Like see, is there some sort of pattern that you can detect in queue and visited and all that stuff? And then from there, we'll be able to write down a loop invariant. The proof I might not write down in full gory detail because it will take too long, but I'll sort of explain how it's mostly done. Okay. Okay, hang on. Okay, so for people on Zoom, just going to share that. All right. I wish I could actually have the document camera and the laptop on at the same time, but that won't work. Okay. Let's move this out of the way. Okay, can everyone see that? Let me see if I can make it a bit bigger. So, and I'll share the link with this. Okay. So what you have here is it's actually a very nice visualization that I found online. So this is just some undirected graph, and this is the parent array, and this is the visited array, and you can see it's all false currently. Right? This graph is connected, so it's convenient. So at the end, basically all of the visited is going to become true, and we'll see what the predecessor is like. And if the BFS queue is actually given at the top over here. Okay? All right. So someone pick a number. 4. Is that a good choice? No, I didn't like that. Another one. 5. Huh? 5. That's a better choice. Okay, 5. So 5 it is. Okay, so we're going to basically run BFS starting from 5. Okay.
What are you trying to connect to?
So, sorry, say it again?
Isn't it the idea that we're trying to get to some destination?
No, so BFS actually gets to all destinations together.
Okay.
Right? So BFS is just going to go through the graph. So BFS starts, what does it look like? What does it look at? It looks at its first neighbor. So it looks at 1, and 1 is not visited. The queue up there is 5. Right? And so 1 goes into the queue. That arrow is basically like the predecessor, right? So it says the predecessor of 1 is 5. So look at the parent array and you see that. And you look at the visited array and you see the T at 1. Clear? Okay. So the next one is 2. It picks that, sticks that in, then 4, 5, 6, 9, 8, then 9. Okay. Yeah? So far so good? So what's in the queue? 1, 2, 4, 6, 8, 9. 5 that's put in blue up there is basically what's been dequeued. What's the head of the queue? Okay. So now my question is, so I'll write this here. You can use your Post-its now, right? And so just to let you know, the way that the code is written, if you look at the adjacencies, they're all sorted by the number. This is just to tell you who's going to be next in the neighbor list. Okay? Okay, what goes next in the queue? So 5 is going to get removed. Right? 5 is going to get removed. And the question is, what goes next in the queue? What goes next in the queue? Is it going to be 2? Is it going to be 0? Or is it going to be 5? So I'll let you talk. You can talk amongst yourselves if you need to look at it. What goes next into the queue? Give you a couple of minutes to look at that. Do I have any extra Post-its? Let me check. Sorry, I don't. But if you come to office hours, I have it in my office. Okay. Yeah? Okay, so what is the answer? What is the answer? Blue, right? So blue is the answer. And why is that? Because you look at the neighbors of 1, and there are 3 neighbors, right? There's 0, 2, and 5. Now, 5, technically, once it goes out, it's going to become visited. I think there may actually be a bug where you didn't make that visited, but anyway, let's see. So step forward. So now you look at 0, and obviously that has not been visited, and so that gets visited, that gets inserted into the queue. Oh. Good. Okay. Okay. 2. Okay, so now let's do this question again. So the question now is, what is going to go into the queue next? You know, the problem with asking these questions is, for me, the right answer is obvious. I don't know how to give good wrong answers. Okay, but Let's do this. What goes next into the queue? Okay, so I'm going to write down a few options. It's going to be 3. Is it going to be 7? Or is it going to be 12? Okay, so I'll get a look at it. Okay, so what is the answer? The answer? Okay, so it is 3. So why is it 3? So we'll see. We'll see what's going to happen now. So we step forward. So 2 is already true. Nothing to do there. 5, so there's a bug over there. That actually should have been true. And actually, for some reason, the source, he forgets to mark that it's true over there. So that's just a visualization bug. So step forward. Okay, so now what's at the head of the queue? It's 2. But then all of 2's neighbors have already been visited. So there's nothing to be done there. So 2 essentially just passes through the queue. 4 just passes through the queue. But 6 is now going to pass through has a neighbor 3. And so 3 is going to go in the queue, and then 10 is going to go in the queue. Yeah?
How do you know if it's going to be 3 or 10?
So the way that the code is written is that the neighbor list is sorted by ID.
Okay.
And this I know because I've played around with this enough to see that. But in general, you're right, it could be either of them. It could be either of them. Okay, so then 3 goes into the queue, and so now the predecessor of 3 is 6. And what this is saying is that you're looking from 6, you're looking at a neighbor, 5, but then this is already in the queue. This has already been visited. There's a bug there. And then, okay, so at this point, you see that the blue arrows are the tree that are being constructed, and that is a subgraph of the whole thing. There are some edges that are not going to be in the tree. For example, the 1-2 edge is not in the tree. The 0-2 edge is not in the tree, so on and so forth. Okay, but now I'm going to ask you a sort of more... does this make sense? Okay, so what are the distances of everyone in the queue? Okay. So what is the distance of 6? Remember, 5 is the source. What is the distance of 6? 1. It's 1. It's 1, right? Because it's the predecessor, so it's 1. What is the distance of 8? Distance of 9? 0? 3? 10? Okay, so what did you observe about the queue?
The distances are not increasing.
Okay, seem to be sorted. Okay. Yeah? Sure, true, but I'm talking about what is it about the queue? I mean, that would be true even for depth first search. No. Okay, let me ask another question. This is a more you have to think a little bit about this question. So we observed that, yeah?
Is it that after the end of the one iteration, the distance of every node in the queue is same?
But that's not true here. There are things of distance 1 and distance 2.
No, after one iteration of the loop completes, after all of the neighbors are added into the queue.
But isn't that already true here? Like at this point, you see that 6 has been dequeued, and all the neighbors of 6 have been enqueued, so it is the end of that loop. It is the end of that loop, yes?
Depth first would be like it would look at 1, and then it would look at 0, and then it would look at 2, and then look at the connection between 2 and 0.
Let's get to depth first search later, right? Yeah, you're right. It'll do something different. Yeah.
There's only 2 distances in the queue, and one of them is always one more. Up to 2. There could be 1 as well. But.
It's
So I'm going to write this down. I'm going to ask you a question. I'm going to phrase this a little differently. Can there be distance 1 and by distance I mean the actual shortest path distance, right? So at this point, we don't know what the shortest path distance of 13 is. At least BFS as is doesn't know. But we as people analyzing the algorithm do know. So can there be both distance 1 and distance 3 vertices in the queue? Okay, so can everyone read this? So hang on. Do you have the answer or the question about the question? Okay. Okay, so I'm going to give you a few minutes to actually think and talk about this. Let's actually take a break right now. Okay, it's been more than 45 minutes. So take a 2 or 3 minute break. When you come back, we'll answer this question. Okay, all right, let's get back. So, by the way, I forgot to bring Post-its today, but I have them in my office. I just hope I have the same colors, but if not, I'll bring them to the next lecture. Okay, so yeah, can there be both vertices of 1 and 3 in Q? You're right, the answer is no. Right, so again, this is where when you study BFS in depth, you realize there's a lot of things that you might not have noticed or known in the past. Right, that the Q only has distance, so okay, actually the question is, why can't this be true? Yeah?
You can only begin on the ones that have 3 vertices when the ones that have 1 vertex have been flushed.
Say that again, sorry?
You can only begin the ones that have 3 vertices.
You mean distance 3?
Distance 3 when distance 1 has been flushed.
Why?
Because it's at the head. Because you have 1, and then you have 2, then you have 3. Then you do all the 1, and then 1 leaves, and then you do all the 2, and then...
Mm-hmm. Yeah?
Yeah, in order to find the vertex, vertex with distance 3, you have to be looking at the vertex with distance 2. And the only time you do that is once you've gone through all those with distance 1.
And why is it that you've gone through those with distance 1? Because the Q is sorted by distance. The Q is always sorted by distance. So those two facts together. The Q is always sorted by distance. So so the Q is always sorted by distance. To see anything with distance 3, you have to process something with distance 2. But because the Q is sorted by distance, everything else in the Q nothing else could be a distance 1 because the Q is sorted by distance. Right? So once you put those facts together, then it's easy to argue. Does that argument make sense? The Q is sorted by distance, and hence, when you look at the head of the Q must have distance 2 to insert anything with distance 3. And then that's the argument. So in general, what happens in BFS is there are only 2 distances ever in the Q. Do you always have 2 distances in the Q? Could you have less? Yeah, you can have less. When do you have less? In the beginning. And actually, if you look at the first time that 5 is processed, it inserts all of its neighbors into the queue. So everybody in the queue has distance 1. And so all the distances are just 1. Okay? Okay, now that we have this statement, so when distance 3 gets into the queue, the head was at distance 2. What do you know about everyone who has distance 1? Yeah?
They're all neighbors of the root.
Okay, so, yes, they're all neighbors of the root. But in terms of these data structures, or in general, instead of 1, 2, 3, I could be thinking of d plus 1, d plus 2. Yeah? You won't visit them ever again because you've already visited them. So therefore, everything at distance 1 has already been visited. And everyone who is not visited must have distance 3 or above. Right? So you have this really nice split. The queue is going to have things of 2 distances. Everyone less than that distance has already been visited, and everyone more than that larger distance has not been visited. And the queue is sorted by distance. So all of these facts together, that's the loop invariant. Does that make sense? I'll write this down. This is a lot. It's a lot to process. But I want to again emphasize or reiterate is why it's pretty challenging to figure this out. Like, you only figure this out if you look at DFS carefully, you kind of pay attention to everything that is going on. Then you discover these facts about the queue, the facts about these arrays. You write that down as a loop invariant, and then you prove the loop invariant, and from the loop invariant you prove the theorem. So the final proof of the BFS theorem is it's 2 pages, maybe 2.5 pages. Okay, so I'll say this again. The queue is sorted by distance. The queue never has more than 2 distinct distances. Everything less than the distance in the queue has been discovered, and everything that has not been visited actually has a distance more than what's in the queue. Okay? So this entire statement is the BFS loop invariant. Okay, so this point. So I'll put the link to this on the website in case you want to look at it. Just stop the share. Move this back. All right. So this, let me write out. So this is also a theorem. It's a loop invariant of BFS. And so I'll just remember, so S is the source, and distance means the shortest path distance from S. Okay. So at the beginning of the while loop, so again, just to jog your memory, the while loop is just this. It's like when the queue is not in. Like at the beginning of that, like think of as soon as you, just before you dequeue. The beginning of the while loop. So I'm just going to say let D be the distance of the head of the queue. Head of the queue. So these four statements will hold. So the first is the queue is sorted by distance. The second, all vertices in the queue have a distance of D or D plus 1. All vertices that have been dequeued have distance D, or I should say at most D. Why didn't I say all vertices that have been visited have distance at most D? Isn't that the same thing? I'll give you a minute to ponder that. Right? So I said all vertices that have been dequeued have distance at most D. Why didn't I say all vertices that have been visited have distance at most D? Yeah?
Because you set the visited to true when you enqueue them, not when you dequeue them.
Okay, and good. So
The vertices that have distance D plus 1 that are in the queue are also visited.
good, exactly, right? So there are things in the queue that have been, the things are in the queue have been visited, and their distance is D plus 1. So if I were to say all vertices that have been visited have distance at most D, that would be false. I could say all vertices that have been visited have distance at most D plus 1, and that would be true. But this is more information, because we're talking about the things that have been removed from the queue. we already know what's in the queue. So there are basically three kinds of vertices, right? There are vertices that have been removed from the queue, vertices that are in the queue, and vertices that have not entered the queue. So so some people have asked me like about the textbook, CLRS, which I mentioned. There's a chapter of CLRS on this. So the question is, do you need CLRS? For the course, technically, no, you can survive without it. But in general, it's a good reference to have as a computer scientist. It's the kind of thing that, like, even before any interview, if you wanted to just skim through the book, it's useful. And it's a very comprehensive book. So it has a lot more than what a few courses will cover. And for what it's worth, it stood the test of time because I used it as a textbook as an undergrad. And I mean, I'm not that old, but I am old. Yeah.
What's CLRS?
Carmen, Laserson, Rifestenstein, which is the textbook.
Oh, okay.
Introduction to Algorithms. Okay. All vertices that have been dequeued have a distance at most d. And then the fourth is that all vertices that are not visited have a distance at least, okay. I'll write this over here. What do I need to put there? Is it d plus 1 or d plus 2? Is it d plus 1 or d plus 2? It's not obvious. Think about it carefully. You can talk if that helps. It's your neighbor.
Well, he said earlier that
It helps to draw a picture, a small one. Yeah. And you work it out, you'll see the answer. By the way, at least means greater than or equal to, right? Just to be clear. Yeah, so, okay, what's the answer? Okay. Why? It's easy enough to stick a post-it above your head, but why? Yeah? Yeah. So you think it's what? It's d plus 1. Why?
Because we know that in the queue there might be some, there are distances of both d and d plus 1, and I'm kind of operating on the assumption that not all neighbors have been.
Yeah, I think that's a pretty convincing argument. Yes.
Yeah, there's like a space where you're still going through copying all of the distant d ones, where there will be unexplored d plus 1 still that has the end.
That you haven't seen, exactly. Yeah.
And like when we were in that lab, the visual, and it was like you have 5 as the source,
Mhm.
6
Yes. So okay, although when I said beginning of the while loop here, I'm not talking about the beginning of that for loop. I'm talking about the beginning of the. So imagine that whole loop has run. Does that make sense? But still, it is true for exactly that reason, right? So maybe the easiest way to think about this is suppose d was 1. So we know that there are distance 1 and distance 2 things in the queue. But as was said, there are many things of distance 1 that the queue has not processed yet. They're just in the queue. You've not dequeued them yet. When you dequeue them, you're going to add their neighbors, which are potentially unexplored. And so those are distance 2 vertices that are out there. Right? I mean, the reason why this becomes subtle is because, if you don't think about it hard enough, you might think, oh, it's d plus 2. And then you try to prove it, and then suddenly the proof breaks down. Right? So all vertices that are not visited have distance at least d plus 1. So this sort of large epic statement is the loop invariant of breadth first search. Okay? So do I expect you to sort of know the proof or memorize the proof? No, that's not the point. Right? Do I expect you to know what the statement is? Yes. Right? Does that make sense? And if anything, I've always asked myself, is it even worth teaching the BFS loop invariant? Because after all, no one is ever going to ask you this question in an interview. Or it's rare that you're in work somewhere and you're like, oh, it's because of the BFS loop invariant. Unless you work as a theorist like me, in which case then you do need to know it. But what I do believe is that regardless of where you go, you're going to have to think about algorithms or think about complex computing systems. And why something happens and why something doesn't happen. And these are good mental exercises to develop that skill. So you're able to look at a process, sort of draw a few pictures, think through it, and generalize. So this is the BFS loop invariant. I'm actually not sure whether I don't want to show a full proof of everything. It will take too long. Maybe I will show some part of it, but maybe the next lecture. I'll think about that a bit. What I instead want to tell you is why does the BFS loop invariant imply the BFS theorem? Okay? So again, proving this, it's a bit of grunt work with induction. Right? You have to look at different cases of what the queue looks like and what happens. But what is important is that just to understand why is it that this statement, the loop invariant, assuming it is true, implies the BFS theorem, which is sort of what we really care about. Questions? So far, so good? Okay. Okay, so let's go ahead. Let's do this. And we'll see how far we get. Okay, so BFS theorem, loop invariant, and I'm just going to read these statements out again, just to sort of give you time to absorb them. So recall, okay. The BFS theorem again was talking about the visited array and the predecessor array, and the fact that if you keep following predecessors, you end up at a shortest path. Right? The loop invariant doesn't seem to talk about the predecessor array. It does talk about the visited array. Right? It doesn't seem to really talk about shortest paths anywhere, although it talks about distances. So where does the predecessor array actually get sort of part of all of this? Yeah?
Well, when we visit a node, then we're also updating the predecessor array.
So essentially when you know what's going to happen at the head of the queue, right? So you know the head of the queue has a distance d. And so then you know that everyone who gets inserted into the queue has that as a predecessor. And so we use that information to talk about shortest paths. Okay, so let's go over this. So So I'm just going to write down, this is a proof of the BFS theorem assuming the loop invariant. Again, one would also have to prove the loop invariant, but that is not something that I'm going to do in full glory. But I do want you to read the statement and understand what it says. So let us prove the BFS theorem using the loop invariant. So the BFS theorem has three parts, one on visited, one on predecessor, one on the actual shortest path, and so we have to prove each of them separately. Okay? So let's begin with one. So one is showing visited true if and only if there is a path from S to V. This itself has two parts. Right? The first part, if visited is true, there is a path from S to V. Then I also have to prove if there is a path from S to V, then visited is true. Right? So there are two sides. It's an if and only if. So let me first prove the first side, which is prove that if visited of V is true, then there is a path from S to V. So each of these proofs ends up becoming an induction. Okay, so the proof is by induction on the number of currently visited vertices at the beginning of the while loop. Okay? Does this make sense? So I'm going to prove it by induction on the number of currently visited vertices at the beginning of the while loop, and I have my loop invariant to sort of help me make this argument. So what I need to argue is that if visited V is true, then there is a path from S to V. And you'll see that this argument actually is not that difficult, because essentially, when does a vertex get visited? When you DQ something and you take a neighbor of it. Right? Actually, let's talk through this and I'll write it. So then how do we prove it? Okay, so remember, we said, when does something get visited? When it is the neighbor. When it's, I guess, okay, so something has not been visited. When is it going to switch from visited to unvisited to visited? When it's the neighbor of the head of the queue. Now, why would this be true then?
You're asking why is it true that?
And what's the proof, essentially? I mean, the gist of the proof. I'll write it down, but what is the gist? What's the main idea? Yeah?
If you keep going through enough predecessors, you can get back to S.
But we have to prove that. Yep, I know, exactly. You have to, like at this point, okay, so here's the problem, right? Formally speaking, all you know is the loop invariant is true, which I will again put over here. So you know that the loop invariant is true, but you don't know anything about these predecessors. So again, this is the part that can often be difficult. You have these intuitions, but those intuitions might be right, they might be wrong. To make it sort of mathematically formal, we have to sort of go through this process. We say, look, this is what we've proven. And then from this, let's see if we can conclude what we actually think is true. There's a difference between thinking something is true and proving it is true. Yeah?
All the vertices in the queue has a distance to S.
Distance to S or, okay, why?
Distance or D or D plus 1.
Okay, fine. So?
So it is connected to
Yes, good. So it is connected to S. So everything in the queue has a distance of D or D plus 1. So it's connected to S. Good. Next. Yeah, what is the next step? Yeah?
When you pop off something from the queue, you already know that's connected to S.
Yes.
E is going to be its child, so that should be connected to
Exactly. So those are the two statements you need. Good. Very good. right? That makes sense? So the first thing is you say, by the loop invariant, everything in the queue has a distance of some d or d plus 1. So it's definitely connected. That means that's what it means to have a shortest path that's some number. So it is already connected. Anything that is visited is going to be the neighbor of the head of the queue. And if a vertex is the neighbor of something that is connected, then it is also connected. Right? So that is sort of, I mean, at some level this might feel a little pedantic. Right? But it is really a process in which you, have any of you done a course in logic ever? Yeah, you have, yeah. So is this sort of making sense? It's kind of like that, right? You're following that logical proof. Was it in the philosophy department or the math department? Math, okay. Math? In? There's a logic course in CS? Oh, we should offer one of those. Yeah, but that's more like Boolean logic. Yeah, no, I meant like propositional logic. Okay, so, okay, good. So I think now you kind of see the argument, so I'm just going to write it down. Just going to do it a little formally. So the base case is only S is visited, right? This is the base case, and clearly S is connected to S. This is just at the beginning. What is the base case? It's like the very first time the loop goes through, and remember, at the base case, initially, the only thing visited is S. So we've made that argument. So now we'll do the induction. So we'll say assume true up to k visited vertices. And so you'll see that the k really, it's just saying that assume true up to some point. Let's just show that the next one is also true. So when the next vertex V is visited. So when does something get visited? When this statement occurs. Right? When vertex V is visited, V is a neighbor of U, which was DQ'd. Right? So we know by the loop invariant property 2, all vertices in the queue have a distance of d or d plus 1. U has some distance to S, so U is connected to S. V is a neighbor of U, so V is connected to S, right? So this is the argument. This is essentially writing down what you said. Has anyone done a course in graph theory by any chance? Okay, so if you have, then you'll see this is sort of familiar. These are the kinds of arguments you make in graph theory courses. So at this point, CS, graph algorithms, and graph theory all sort basically meet. Okay? Okay, so does this argument as written make sense? Okay. So this proves, and so this is sort of completes the proof. This completes the induction. Okay, then we need to do the other part, which says if there is a path from S to V, then visited V is equal to true. Does that make sense? It's a bit trickier. Now you think about it, what is the argument for this? How do you know that BFS is always going to discover? That make sense? Okay, homework. That's it. First homework problem, done. Move on to the next one. First, let's talk about it, and then I'll make you write the argument. Okay, why? What is the proof of this? Give me an argument for why. If there is a path from S to V, so S is connected to V, then visited V is true. Yeah, yeah, you. Behind.
The second argument of loop invariant.
Second loop invariant, sorry, I would.
It says that. We don't cancel anything. But we said that like the predecessor or like visited is null, or I guess it's false by default if there is no path from S to V.
That's only if you've proven it.
Okay, I'm gonna look into one.
That's the second statement of the BFS theorem, not the loop invariant. This is called proof by circularity. So how do you prove this? Look at that. How do you prove that? Look at this. Like done. Right? As long as you have enough chains over there, no one will know the difference. Yeah. Yeah?
Maybe it could be like induction on the number of visited nodes.
Okay.
Right, and say that like if we haven't reached all of them, right, then there must like or how to say it. If we're at like at one step, right, and we haven't reached all of them, then there must be a path to another one. And if there is no such path, then we must have reached all the like nodes that are in the connected component.
Yeah, okay. I mean, sort of, kind of. Yes. Yeah?
You can say that, like, so assume true for K, and then on whichever node you're on, you know all of its neighbors will get visited.
Sure.
And then, so like, if all neighbors are visited of all things, then all of them are connected.
Yeah, but that sort of seems more like the first step, not this. What you're saying is, what you just said was somewhat of a restatement of this. What you're saying is that if visited is true, then there is a path. But to argue sort of the converse of that statement, it's I mean, it's a little subtle. Yeah. The loop invariant? Yeah, I wish I was in there are some classrooms that have 2 document cameras. And that's actually what I need for this course. But anyway, yes.
With number 3, all the vertices that have been in the queue has distance at least V. So we can start saying that S is like the starting point. So if there's a path from S to V, then it means that V that is a neighbor must have a distance of at least equals 1 because of.
But you don't even. Why do you know that V is going to even end up in the queue? Almost. The thing is, yeah?
Because V's parent is in the queue.
Why? They say that, like, an argument is what you use to convince a reasonable person, and a proof is what you use to convince an unreasonable person. Right? Yeah?
We are saying that the first part is true.
This?
There is a path from S to V. So we know that there is a path from
In the graph, but not in the BFS structure. There is a path in the graph, but that doesn't mean there is a path in the predecessors. If there's a path in the predecessors, then it's obvious. Yeah?
Is it because we only set from false to true while it's in that for loop in the program?
But that's just the induction part of what you just say.
I proved the converse. I proved that if visited v is true, there is a path from S to v. I didn't prove that if there is a path from S to v, then visited v is true.
Yeah, but we can, with the base case, we can say that there is a path from S to S. So we have the predecessor. Then just add the next one. And there is a path from the next one to the neighbor of S to V. And then we can induct over there.
Okay, so how do we formalize that? Yeah?
One thing, maybe like if there's a path from S to V, then V has some distance.
Okay, good. So therefore v has some distance. Yeah? Then what? Yeah?
And then we can perform maybe induction on the distance and try and like...
You can do induction on the distance. Let me also state it by contradiction. Say, suppose it was false. So let me just say this. Suppose it was false. So there exists a vertex from S to V such that visited V was not visited. Okay? Find the vertex. There is a vertex of minimum distance of that kind. Right? So everything closer than that was visited. But if you visited everything closer than that, you must have visited the neighbors of that. And therefore this gets visited. Does that sort of make sense?
Can we go over this again?
Yeah, I'll say it again.
Like at the beginning of the next class?
Sure. What? Oh, we're off. We're out of time. Okay. So, sorry. End of class. We'll go over this the next lecture.